Hello and welcome to the session on the strength of materials. So in this session we'll be discussing related with the bending stresses and the shearing stresses. I am Professor Khond, working in the Mechanical Engineering Department at KK Institute of Engineering Education and Research, Nasik. So we start with the bending stresses. So picture is being shown over here. So we are having the loading diagram. In the loading diagram, this is the loading diagram, this is the shear force diagram, and this is the bending moment diagram. So in the loading diagram we are having a simply supported beam and a two point load or the concentrated load. So this is acting at a point, so it is point load, and this is also acting at a point load. So this is the hinge beam and this is the roller support, hinge support and the roller support. So it is acting at a distance A. So whatever the shear force diagram for this particular case will be getting like this, and the bending moment diagram will be like this. Now what is bending stresses? Now if a constant bending moment, that is no shear force, acts on the some length of a beam, the stresses set up on any cross section on that part of the beam constitute a pure couple, the magnitude of which is equal to the bending moment. So in this section we can see a constant bending moment is being acting within this particular length of the beam. So constant bending moment. In that case, if you see the shear force diagram, there is no shear force. So it will constitute a couple and it is equal to the bending moment. Okay. So the internal stresses that develop in the beam are known as flexural or the bending stresses. So this is the case where the shear force is equal to 0 and pure bending moment and constant bending moment, pure bending and the constant bending moment. That is the three particular cases for the bending stresses. Okay, now coming to the bending or the flexural formula. For the flexural formula we are having the renowned flexural formula, that is M by I is equal to sigma by Y is equal to E by R. That is, so let us take a section of the beam and it will that particular length of the beam. So the length is dx and the pure bending moment is being acting over here. So that pure bending moment is M over here. Okay. So NA means the neutral axis. So whenever the pure bending moment is acting, so the beam will try to bend. So it is a portion of the beam before bending. Okay, it is a portion of the beam before bending. NA being the neutral axis, which is the axis which is not stress at all. We are having the strain but which is not stress at all. So that is what we can say, it is a neutral axis. So the particulars of the bending formula: M, that is the Banksian bending moment in Newton mm. I, moment of inertia about neutral axis, mm to the power 4. Sigma, that is the bending stresses, Newton per mm square. Y, the distance of outermost fiber from the neutral axis. So it is being shown over here Y, but we are having the, for this particular formula we are having the distance of outermost fiber from the neutral axis. So this is the example being given, that at this section the Y being taken, but for the formula we are having distance of outermost fiber. So either this point or this point, so upper or the lower. So because of this bending moment, what will happen, the upper fibers will be in compression, lower fibers will be in tension. Okay, so E being the modulus of elasticity of material, that is in Newton per mm square. R is the radius of curvature. So again in the bending stresses we are having the formula, that is section modulus Z is equal to I by Y max. So Y max is equal to YT on the tension side. So let us say in the tension side, so from this point to this point, so that is tension side. So Y max is equal to YT and Y max is equal to YC on the compression side. So for this particular case, this may not be the always the case, but for example you have taken, so from the neutral axis to the outermost fiber, so that distance is YC for this particular case, that is compression side. So this is the standard formula for the section modulus. So Z is equal to I by Y max. Y max, that is the maximum distance of the outermost fiber. Now this is the portion of the beam after bending. We are having the R, that is the radius of curvature, angle theta we are having. So pure bending moment M, neutral axis will be flowing like this. Okay, now neutral axis will taken. So is the neutral axis. So this is the cross section of the beam which is subjected to the pure bending moment. So upper fibers are in compression, lower fibers are in tension. So this is the compression, this is tension. So consider the topmost region, top region in compression, lower region in the tension. So that is what the case, what I have discussed. Okay, now these are what the bending stress distribution diagram. So these are for the different sections. So first section is the rectangular section. We are having the rectangular section. Okay, so for the rectangular section, this is the bending stress distribution diagram. So this goes like this and this goes like this. Either it may be a tension or it may be a compression. So sigma may be tension, sigma may be compression, depending upon the loading, so whether the loading in upward direction or whether the loading in the downward direction. Okay, so depending upon that, sigma may be tension, sigma may be compressive. So for the bending, so nature, we can say that the nature of the bending stresses, that is sigma b is the bending stresses. So the nature of the bending stresses may be the two cases, one either it may be a tensile or it may be a compressive. So sigma b may be sigma t or sigma b may be sigma c. Okay, so for the circular section, so this is the circular section of the beam. So again the bending stress distribution diagram will be the same. Okay, at the neutral surface will be like this. So here it is sigma, here it is sigma. It may be sigma t or sigma c, it may be sigma t or sigma c. For the triangular section, so neutral axis will be passing through over here at a distance of h by 3 from the base. So at a distance of h by 3 from the base, so it may be maximum over here, this may be sigma max over here, or it may be sigma mean over here. So for the triangular case, it may be variation. So that is 2h by 3 and h by 3, that is the distance being shown over here. Then for the unsymmetrical I section, so it is unsymmetrical. So this section is symmetric about y axis, but it is unsymmetric about x axis. For x axis it is unsymmetric, for y axis it is symmetric. So and normally we are considering with the x axis. So whatever the I, that is moment of inertia, normally it is related with the Ixx. Okay, so for unsymmetrical I section, these are the bending stress distribution diagram. Yt being let us say Yt, and actually it should be Yc. Okay, then for the T section, again it is a unsymmetrical section. It is unsymmetrical. It is symmetric about y axis but unsymmetric about x axis. So for this unsymmetrical section, so this is what the case. So sigma c being written over here, sigma t being written over here, but depending upon the loading diagram, it may change. It may be sigma t or it may be sigma c, or it may be yt or it may be yc. So depending upon the loading diagram, it may change. So then coming to the shear stresses in the beams. So when a beam is subjected to non-uniform bending, both bending moment M and the shear force V, or we can say shear force S. In some books it is being taken as S, in some books it is being taken as Q, in some books it may be taken as F, but we are following with either V or either F. So whenever the beam is subjected to non-uniform bending, so both bending moment, that is M, and the shear forces acts on the cross section. The normal stresses sigma x associated with the bending moment are obtained from the Flexure formula. Okay, the distribution of shear stress associated with the shear force. Now we have to consider the case of non-uniform bending. In the previous bending stresses we have taken the case of uniform bending. Here we are taking the case of non-uniform bending. So when a beam is subjected to transverse loading, a normal and the shearing stresses result in the beam. The influence of shearing stresses in the beam does not disturb the influence of bending stresses. So that means that if the shearing stresses acts on the beam, so it does not disturb the influence of bending stresses. So in a beam, whenever there is transverse loading, whenever there is non-uniform loading, there may be a combination of normal, that is the bending, or the shearing stresses. There may be the combination of two stresses, but shearing stresses does not influence the nature of bending stresses. So let us say this is the particular case, so this is the section of beam. We have taken the V being acting, that is shear force being acting. This is the dimensions, width and height, and this is a section of portion of the beam. So because of that shear force, so it is being acting within the length, within the width of the beam. So if you take that particular section, so shear stress on one side of the element are accompanied by a shear stress of equal magnitude acting on perpendicular faces of an element. So you can see over here, so one side of so if you take the section, so shear force on one, shear stress is on one side, it is being accompanied by shear stress on of equal magnitude acting perpendicular of an element. So thus there will be a horizontal shear stress between horizontal layers of the beam as well as transverse shear stress on the vertical cross section. You can see over here, you on both sides we are having the shear stresses. So it is being accompanied with the, so that portion is being called as complementary shear stresses. So at any point within the beam, these complementary shear stresses are of equal in magnitude. So these are the complementary stresses. So these are the shear stresses and these are the complementary shear stresses. So because of that we are having the horizontal shear stresses as well as the transverse shear stresses. And what we are going to decide is, we are going for the shear formula, and this formula is nothing for the horizontal shear stresses under the non-uniform bending. So this is the formula for the horizontal shear stresses for non-uniform bending. So tau is equal to SAY upon BI. So let us take the case. So it is the portion, so it is non-uniform bending. So in the previous case it is M and M, but because of non-uniform it is M and M plus DM. So S, that is shear force, S plus DS, that is the non-uniform shear force. So non-uniform shear force, non-uniform bending. So because of that we can take the F1 and F2. These are the normal stresses, and Q, that is the shear stresses. So we have taken the layer, we have taken one layer at a length of y1. Okay. So again in the in the side view we can take area dA, which is under consideration, and the distance y. So area at a distance y that can be taken. So these are the particulars for the shear formula. Tau, that is the shear stress at given section in beam. I, that is the moment of inertia of the whole section about neutral axis in mm to the power 4. A, that is the area of beam, area of the section under consideration, area above the section under consideration. Y is the centroidal distance of area under consideration from the neutral axis. S is the shear force acting at a given section of the beam. Then B, that is the actual width of the beam. B is the actual width of the beam or the section. So these are the shearing stress distribution diagram. So various sections are being shown. Beam section is being shown. Shearing stress distribution diagram. For the rectangular case, so at this point it is 0, at this point it is 0, at the neutral axis it is maximum. So it is conflicting with the bending stress distribution diagram. At the bending stress distribution diagram, you can see you can see that at the outermost layer the bending stresses are maximum, and at the neutral axis it is 0. So it varies, but in this case it is 0 at the top level, 0 at the bottom level, and maximum at the neutral axis, because we have taken that if you want to take the shear stresses at this point, so we have to consider the area, which is directly proportional. So area above the section, so as there is no area above this particular level, so we have taken it should be equal to 0. Okay, area above the section, that is equal to 0, area below the section, that is will be equal to 0. So that's why at this point and the topmost point and the below bottommost point it is equal to 0. So for the circular section, this is the at the neutral axis it is maximum. Okay, so for the triangular section at the neutral axis which will be like this, and this is the neutral axis over here, this is the neutral axis, and this is the maximum stress. Okay, so neutral axis, this is the neutral axis, that is 8 by 3 F by BH, and maximum shear stress, that is 3 F by BH. This is formula. So there may be the different formula for the different cases. So now for the I section, this is the variation. So why this is variation? Because at this point it is 0, at this point it is 0. Now at this particular level there will be two width, and that width is indirectly proportional for the formula. Tau is equal to SAY upon BI. So B is inversely proportional. So if B increases, tau decreases. If B is lower, then tau will be more. So for this particular width, stresses will be more. For this particular width, so from this point to this point, so the stress will be less. So there will be two width. So that's why it is there are two stresses. So at this level also it is varying. Okay, because the area is more, so the stresses will be more. Because from here we have to take down the area, whole area, so that's why the stresses are more. Okay, so it is symmetrical. So upper section and the lower section, these are symmetrical. For unsymmetrical section, so at this point 0, at this point, at this level we are having the two stresses, one for maximum width, another for lower width. So at neutral axis more area, so that's why maximum stresses, and here there is 0, so it is varying like this. So that's it. So these are the reference for my presentation, for my video. So these are the references. So thank you for listening. If you like the video, then like it. Also please subscribe my YouTube channel by pressing the bell icon button and never miss the updates. So thank you.